Hello, friends. Here we are. This is the last section of the last unit of the year. Woohoo! 8.8, we are going to talk about the logarithm graph and the inverses of logs, which we already know is exponential. The inverse of an exponential equation is a log. The inverse of a log is an exponential. So we're actually going to start with inverses. We have found the inverses of almost every single parent function that we've talked about this year, and an inverse is a two-step process. Step 1, switch the x and y. Step 2, solve for that new y. So that's exactly what we're going to do. Notice in example A, we have an exponential equation that we're going to find the inverse of, so that inverse will be a log. And then in example B, we're starting with a log, so the inverse will be an exponential. So here we go. First step is switching x and y. So this is now x equals 11 to the y plus 1 minus 4. We want to isolate the term that has the exponent in it, so the exponential term. So to do that, we're going to add the 4. And then we kind of get stuck, quote unquote. So at this point, this is where we rewrite into log form. Log base 11 of x plus 4 is equal to y plus 1. Okay, last step to get y by itself is to subtract 1 from both sides. So when I do that, I am going to get log base 11 of x plus 4 minus 1, and that is the inverse of our function. We got y by itself, so that is it. Final answer. Okay, and in a little while, you're going to be able to tell what our transformations are in this log equation. Okay, now let's do the opposite, starting with a log equation and finding the inverse, so we know our answer is going to be an exponential. So first step, switch the x and y. Second step is I want to isolate that log term, so I'm going to divide by 2. And then I'm going to rewrite this in exponential form because I'm trying to get to the y, which is in the argument. Because I'm taking the natural log of something, I know the base of that is e. So e to the x divided by 2 power is going to equal the argument of y plus 6. To get y by itself, oh, sorry.
Test 1, 2, 3. Test 1, 2, 3.
Well, that was fun if you heard that. Okay, so to get that y by itself, all we need to do is subtract 6. So e to the x divided by 2 minus 6 is equal to y, which is the inverse of our function. And that's it. Now, this is an exponential equation, which we've already talked about. So you should be able to look at this and know that there is a horizontal stretch because that 1/2 is being multiplied to the x and the exponent. So it's a horizontal stretch. And then that minus 6 at the back end would be a shift down 6 units. All right. So like I said, the log function is the inverse of the exponential function. So not only are we seeing that algebraically, but we're also seeing that on a graph. So let's just quickly go over how to graph the exponential functions. Remember, it's all dependent on what my base is, if it's going to show growth or decay. So when that base is a number bigger than 1, that's going to show growth. And when that base is a number that's less than 1 but bigger than 0, it's going to be showing decay. Remember, your base can never be 1 because 1 raised to any value is equal to 1. Therefore, you'd be getting a straight horizontal line, which is not an exponential function. Okay, so for the exponential pattern of graphing, it was always 0, 1, 1, your base, 2, your base squared, -1, 1 over the base, and then -2 would be 1 over the base squared, and that pattern would continue, right? So if my base is bigger than 1, 0, 1 would be here, 1, the base would be a number bigger than 1, base squared would be all up here, and then -1, 1 over the base, we'd be getting closer and closer and closer to that value of 0 because we have an asymptote there. So remember, for exponential functions, you do have a horizontal asymptote at x equals 0. I'm sorry, y equals 0. Ooh, y equals 0. Domain was always negative infinity to positive infinity. Range was dependent on if there was any kind of transformations that flipped it or anything like that or shifted up and down. So for the parent function, the range would just be 0 to infinity. Let's quickly look at decay. Our pattern of graphing was the same. It was still 0, 1, 1 the base, 2 the base squared, negative 1, 1 over the base, negative 2, 1 over the base squared. Where b is a number that's less than 1 but bigger than 0, so 0, 1 is still here. 1 comma the base is going to be going down because it's less than 1, and negative 1 over the base would be a number bigger than 1. So again, showing that decay, still have that horizontal asymptote at 0. Domain will always be negative infinity to positive infinity, and then of course range is affected by some transformations, but we don't have any, so still 0 to infinity. Well, if the log function is the inverse of the exponential, then you know inverses, we switch the x and y. So our pattern of graphing is going to be quite the opposite of the pattern of graphing for exponentials. So instead of 0, 1, 1, the base, etc., it's now going to be 1, 0, base, 1, base squared 2, 1 over the base, negative 1, so on and so forth. Another major change in the graphs is that you obviously would not have a horizontal asymptote anymore. You are now going to have a vertical asymptote. The x and the y switch. So if my asymptote of an exponential was y equals 0, then the asymptote of a log is x equals 0. So again, your base is going to be a number if it's bigger than 1. Not necessarily, I mean, it's showing growth, but I am going to show you the differences between what kind of number your base is. So points here, like I said, are going to be the opposite. Instead of 0, 1, it's 1, 0. Instead of 1, the base, it's going to be the base, 1. And then instead of negative 1, 1 over the base, it's going to be 1 over the base, negative 1. Okay, you just switch the x and y. Now we have that vertical asymptote at x equals 0. 1, 0 is here. My base is a number bigger than 1, so I'm going to be going to the right and then up 1. And then 1 over the base would be a number less than 1 and then going down 1. So we see this shape of our graph for the log function. This time, my domain, the leftmost value I can use is 0, not including it, and I can go all the way to infinity. The range this time is starting from negative infinity and going all the way to infinity. Remember, another characteristic of inverses is that domain and range get switched for inverses. So it makes sense that these are the correct domain and ranges here. Okay, and then let's try it if that number is less than 1 but bigger than 0. Still 0, 1, base, 1, 1 over base, negative 1. But this time, when we graph it, 0, 1 is here. 1, 0 is here. If I go to base, 1, and base is a number less than 1, then I'm going to be closer to that value of 0 and going up. And then 1 over a base is going to be a number bigger than 1, and that's negative 1. So it's going to look something like this. Okay, domain is still domain is still 0 to positive infinity. Range is still negative infinity to infinity. Okay. So it does show growth in that first one. If I read it from left to right, I am increasing from left to right, so that's growth. And the second one is also showing decay. I'm going down from left to right, so that's also showing decay, which makes sense based on what the value of our base is. Okay, so like I said, great news. You know how to find inverses. Therefore, you know how to find or graph the log function because it's the inverse of the exponential, and you know how to graph the exponential function. So we're going to graph these two. These are basically what those parent functions would be. Log of x, so that's a base of 10, and then the natural log of x, so that's that base of e that we've talked about before. That one's going to be more of an approximation when graphing because e is an irrational number, but for the log of x, it's going to be a little bit more easier to graph because we know the base is 10. So sketching the graph of log of x, I'm going to go with 1, 0, base, 1. If I wanted to, the base squared, 2, 1 over the base, negative 1. Well, base squared, 100, there's no way that I can fit that on my graph, but if you want to see that in case you do get a smaller base in the future that you could fit that on the graph. Vertical asymptote at 0, 1, 0, 10, 1 would be here, and then 1/10, negative 1 would be something like this, and then it'd be a really sharp kind of turn there. Domain, 0 to infinity, range, negative infinity to infinity. Over here, same thing, base is e, so 1, 0, e, which is approximately 2.71. E squared, if you wanted to, was about, I think it was like 7.4, and then 1 over e, which would be about 1/3. negative 1. So again, no shifts, so vertical asymptote is still at 0, 1, 0, e comma 1, so somewhere about right there, somewhere about right there, and somewhere about right there. And there you have it. There is your log graph, 0 to infinity, negative infinity to infinity. All right. So, of course, we'll see this transformation chart for the last time this school year. You know, anything happening inside your parentheses is going to be horizontal. Anything happening outside the parentheses, in front or behind that argument, or in front of the log or behind that argument, that's going to be vertical. So remember, we're dealing with the log graph. So anything happening within the argument, that would be inside the parentheses, is horizontal. So if I want to shift to the right, I'd see something like log of x minus some number. Shifting to the left, log of x plus some number. If I have a horizontal stretch or compression, it's going to look the same. It's just dependent on what that value of b is. That's going to look like log of some number times x in the argument. And then if I reflect over the y-axis, log of negative x as the argument. So all of those things happening inside the parentheses are horizontal. Everything in front of the log or behind the argument is going to be vertical. So if I want to go up, I'm going to have the log of x plus some value. Shifting down, the log of x minus some value. Vertical stretch or compression is going to be some number times the log of x. And then a reflection of the x-axis is going to be a negative log of x. Okay. Very similar to the exponential parent function. When you shift left, right, up, down, that point is not a point on your graph. That is your new origin point. So I'm going to do x marks the spot, and then I know my asymptote goes through that x. For a log graph, we do not have a horizontal asymptote. We have a vertical asymptote. That is one of the main differences on our graphs, okay? So what I'm going to do for these next two is I'm going to identify my base. I'm going to identify the transformations, and then I will sketch the graph and find domain and range. So over here in this first problem, my base is 2. My transformations, I see a 3 out in front being multiplied, so that is going to be a vertical stretch. Inside the parentheses where the argument is, I see x plus 4, so that means I shifted left 4 units. And then after that argument, I see a minus 1, so I went down 1 unit. So my starting point is going to be shifting left 4, down 1, x marks the spot. Through that x, I'm going to put my asymptote, which is a vertical asymptote for log graphs. Okay, so from the point negative 4, negative 1, now I'm going to write my pattern of graphing. 1, 0, base 1, if you want to put base squared 2, and then 1 over the base negative 1. Now I need to go back and see if there's any other transformations that I need to apply, and there is. I have a vertical stretch. Therefore, that y column, that second column, all those values are going to get multiplied by 3. So this is now 3, 6, and negative 3. So from x marks the spot, I'm going to go right 1 up 0. From x marks the spot, I'm going to go right 2 up 3. From x marks the spot, I can go right 4 up 6. From x marks the spot, I can go right a half down 3. And so when I connect those dots, I do get that log graph. Domain, the leftmost point, is going to be from negative 4 all the way to infinity. So the shift left or right is going to affect your domain. Range will always be negative infinity to positive infinity. Remember, the domain and the range got switched from exponentials. If the domain of an exponential was always negative infinity to positive infinity, then the range of a log will always be negative infinity to positive infinity. Okay, let's do it again. Over here, I can identify my base first. However, something is catching my eye in that argument. When you have a b value, remember you need to factor it out. So I'm actually going to rewrite this before I forget. Negative log base 3 of 2 times x plus 5 plus 4. Base is still 3. That doesn't change, but I just didn't want to forget to factor out that b value before I list my transformations. So base is 3. First thing I see is a reflection over the x-axis. Then I see that horizontal compression that I had to factor out. a shift to the left 5, and a shift up 4. So from the starting point, -5, +4, I'm going to go ahead and put my X marks the spot, vertical asymptote running through there. Okay, pattern of graphing, 1, 0, base 1, base squared 2, 1 over base -1. I need to reflect over the x-axis, so these numbers are going to take the opposite value. And I need to horizontally compress, so I'm either going to multiply by the reciprocal or divide by that number. My number is 2, so dividing by 2 or multiplying by 1/2. Okay, so from my X marks the spot, I'm now going to go right a half, up 0, right 3/2, which is 1.5, down 1, right 9 over 2, which is 4.5, so 1, 2, 3, 4.5, down 2, and then I could go right a 1/6, up 1, so really close to that asymptote. And so there's my graph. Shifting left 5 units means my domain is going to be from -5 to infinity. Range is always -infinity to +infinity. Okay. Now we're going to gonna combine these two things. We're going to find the inverse of the equation, and then we're going to graph both of them on the same coordinate plane so that you can get that visual. Remember that inverses are reflections over the line y equals x. So having both of them graphed on the same coordinate plane is going to give you the visual of seeing that reflection. Okay. So the first thing I'm going to do is I'm actually going to find the inverse algebraically, graph that one, and then I can go back and graph the original. Obviously, it doesn't matter the order that you do this. So in order to find the inverse, I'm going to switch the x and y, and then solve for y. And remember, we're trying to get the inverse, but we are going to have to go back and graph that inverse. So I do want to kind of keep it in that skeleton of transformations to make my life easy when I go back and graph it. So our goal here is to isolate the log term because y is in the argument and I need to solve for y. So to isolate the log term, I'm actually going to subtract 3 first. And then I want to get rid of that 1/2 in the beginning. So to get rid of that 1/2, I'm actually going to multiply both sides by 2. You could divide by 1/2, but I think it's going to be easier to multiply both sides by 2. So now I have 2 times x minus 3 is equal to log base 2 of -y minus 2. Now my log is isolated, so I can rewrite it in exponential form. Base is 2 raised to the 2 times x minus 3 power is equal to the argument of -y minus 2. My goal is to solve for y, so to solve for y, I need to add the 2. So 2 raised to the 2 times x minus 3 power plus 2 equals -y. Be careful with this last step. You're dividing by a negative or you're multiplying by a negative. It doesn't matter which one. Everything on this left-hand side is getting multiplied or divided by that negative. So let's think about it. If I multiply, negative times all of this, that negative is going to get distributed. So that positive 2 at the end actually does change to a negative. So this is now negative 2 to the 2 times x minus 3 power minus 2 equals, and that's my inverse. Okay, so this is my final answer, which is an exponential, and I can clearly see all the transformations that were applied to it. Okay, so I'm going to make all this a lot smaller so I have room to write all the other things. Okay, so this is my inverse that I'm going to be working with. So I'm going to go ahead and talk about graphing that first. This is an exponential with a base of 2. It has been reflected over the x-axis, horizontally compressed, shifted to the right 3 and down 2. So starting from the point 3, -2, this is exponential, so it's 0, 1, 1 base, 2 base squared, -1 over the base. I have already taken care of my shifts. Now I need to do my reflection and my horizontal compression. Reflection was over the x-axis, so change all these to the opposite sign. Horizontal compression, dividing by that 2 or multiplying by 1/2 gives me those values. So starting from 3, -2, x marks the spot. This is exponential, so it has a horizontal asymptote going through that point. Now I graph these points. 0, -1, 1/2, -2, 1, negative 4, and then negative 1/2, negative 1/2. Oh, right there. So I'm getting this for the inverse of that function, which is an exponential. Now I need to go back and graph the original. I'm going to rewrite this because I do see a b value there. So this is 1/2 log base 2 of negative times x plus 2 plus 3. So I have vertically compressed. I have reflected over the y-axis. I've shifted to the left 2 and up 3. So from the point negative 2, positive 3. Negative 2, positive 3 is here. That's going to be a vertical asymptote because it's a log graph. Now I have 1, comma 0, base, comma 1, base square 2, 1 over the base negative 1. I have a vertical compression, so my y values are going to get multiplied by 1/2. And I have a reflection over the y-axis, so these signs get changed to the opposite. So now from that x marks the spot, I'm going to go left 1 up 0, left 2 up 1/2, left 4 up 1, and then left 1/2 down 1/2. Connect the dots. If you need to see that reflection, I like to sometimes put that line of y equals x, and now I can better see that the blue has been reflected to get the green, or vice versa. So algebraically, I know they're inverses of each other, and graphically, I know they're inverses of each other as well. Okay, let's do it again. So in A, we started with a log, we got an exponential. Now we start with an exponential, so we're going to get a log as the inverse. So I'm going to go back, and I'm going to find that inverse first. You don't have to do that. You can graph this as is. So switch the x and y. Isolate the term that has the exponent. What is being raised to the power is 3. So I need to isolate the 3 to the y minus 1. So first thing is subtract the 4. Divide by the negative 2. So I'm going to actually write that as multiplying by a negative 1/2, because I know I need to graph this at the end, so I want to make it look like transformations. And then I'm stuck, so I rewrite this as a log base 3 of negative 1/2 x minus 4 equals y minus 1. Last step is just to add that 1. So log base 3 of a negative 1/2 times x minus 4 is equal, plus 1 is equal to the inverse of that function. Okay, so this is what we're working with. To log graph, I have reflected over the y-axis. I have horizontally stretched. I have shifted to the right 4 and up 1. So from the point 4, 1, this is now a log graph. So following the log pattern. Dang it. Try that again. Okay. Whatever, I give up. Okay. It's going to be 1, 0, base, which is 3 here. So 3, comma 1, base squared 2, 1 over the base negative 1. I need to apply the other transformations. I have horizontally stretched, so I'm dividing by that 1/2. And actually, I've reflected over the y-axis as well, so I can do those two things together. So this is now going to be negative 2, negative 6, negative 18, which won't fit on my graph, and then a negative 2/3. So from the point 4, 1, x marks the spot, log graph, so a vertical asymptote. I'm going to go left 2, up 0. I'm going to go left 6, up 1. And then I'm left 18, up 2 won't fit. Left 2/3, down 1. And so I get something looking like this. The original problem was an exponential. So I have reflected over the x-axis. I have vertically stretched. I have gone to the right 1 and up 4. So from the point 1, 4, 1, 4 is here. X marks the spot. Horizontal asymptote because it's an exponential function. 0, 1, 1, the base, 2, the base squared, negative 1, 1 over the base. Reflecting over the x and vertically stretching, I can do both of those at the same time, multiplying by negative 2. Okay, and so from that x marks the spot, I'm going to go down 2. I'm going to go right 1, down 6. I'm going to go left 1, down a third, or 2/3, excuse me. Left 1, down 2/3. So then I get something like this. Again, I suggest kind of drawing that line y equals x so that you can clearly see they have been reflected over that line to create the other graph. All right. Okay, so for something like this, it says find the domain of this log function. Well, there's no way that I would expect you to algebraically do something to get it in terms of transformation. So this is not anything that you would draw, right? Everything happening inside those parentheses there is horizontal, right? That +3, you can easily tell me that it's been shifted up 3, but going up 3 doesn't affect the domain. So what affects the domain? Let's go back up. Like for these kinds of problems, your domain was affected by your shifts left and right. Well, when I see something like 3x squared minus 7x minus 6 in my argument, I don't really know where to start. What I do need to know, though, is that my domain is going to be positive, right? My argument needs to be positive. So I can actually just make this argument positive. I need to ensure that it is greater than 0. And that's what I'm going to solve, okay? Now, this is kind of throwing you back to quadratics. When we had inequalities with quadratics, you're going to solve that left-hand side like normal, right? So there is no GCF. It is factorable. Factors of -18 that add up to -7 are going to be a -9 and a +2. I am going to split the middle. So now I have 3x times x minus 3 plus 2x minus 3. So I have 3x plus 2 and x minus 3 greater than 0. At this point, this is where it changes. I don't just have one factor equal to 0 and the other factor equal to 0, or set one factor greater than or equal to 0, or whatever. At this point, what we need to do is we still need to find the zeros of those factors. So this is going to be a -2/3 and this is going to be a +3. At this point, we need to do a sign test. So I'm going to pick a number from the left, in the middle, and on the right, and plug it back in to see which values are going to give me positive solutions. So the easiest one in the middle is 0. 0 is a number between -2/3 and +3. When I plug in 0 for x in both spots, 0 times 3 is 0. 0 plus 2 is 2. 2 is a positive number. Times 0 minus 3 is -3, which is a negative number. A positive number times a negative number is a negative number. Negative numbers are not greater than 0. So anything in this region between -2/3 and 3 is a negative number, which is what we don't want. We want our argument to be greater than 0. Now, you know that what we have in the argument is a quadratic. So at this point, you technically should know that on either side, the left and the right, they're going to be positive numbers, because on a graph, you're seeing something like if I have a 0 at -2/3 and a 0 at +3, and I know that in this region, it's below the graph, then my quadratic is here, right? But if you don't remember that, you could pick a point over here, pick a point over here, plug it in, you're going to get positive values. So positive times a positive is a positive, or maybe you get a negative times a negative, which is still a positive. So that means my domain for this is going to be, I want the numbers from -infinity to -2/3 and from 3 to infinity. Done. Okay. That is it, ladies and gents. Go and do your practice.